I think we can start. Welcome everyone to the second Tuesday seminar of this semester. We are very happy to host our own Przemek Mroz. Przemek graduated from this university. He spent some time in Caltech at his postdoc, and he came back leading two great projects related to microlensing and also black holes. And today he's going to share with us his results. And the title of the talk is Toward the Mass Function of Black Holes with Modern Observations of Microlensing Events. Przemek, the floor is yours.
Thank you for your introduction and this invitation to give this talk. So today I would like to tell you about using gravitational microlensing to study black holes in general. Okay, so I'm pretty sure that most of you have seen this picture, which shows the known black holes and neutron stars that have been discovered during the whole history of astronomy. And as you probably know, most of these objects have been detected thanks to gravitational wave detectors LIGO and Virgo. They are shown here with blue circles. What is really striking, what I find really striking when I'm looking at this picture is that the masses of black holes detected by LIGO and Virgo are on average several times higher than the masses of black holes that were known previously from electromagnetic observations. They are shown here. So we are finding black holes that are too massive. We are finding black holes with masses significantly higher than 100 solar masses. But we are also finding objects with masses between the masses of neutron stars and ordinary star mass black holes. So I think explaining this picture is one of the biggest and one of the most important tasks for astronomy in the next years. Of course, as we know from last week's lecture, trying to understand that picture is really difficult, because if you want to understand the population of black holes detected by LIGO and Virgo, we have to understand several physical processes. For example, we have to understand the evolution of massive stars. We think that black holes come from massive stars. We have to understand the formation of compact objects, black holes and neutron stars in supernova explosions. We have to understand the engines of supernova explosions and processes that undergo during these explosions. We have to understand the angular momentum transfer in massive stars. We have to understand the binary stars. For example, the efficiency of mass transfer in binary star systems. You have to understand the evolution of the common envelope systems, physics of stellar mergers and collisions. And on the top of that, you have to understand the impact of the environment, the impact of the metallicity, stellar density on all of these processes. So arguably, it's hard. And whenever we have such a complex problem, it's one of the good ideas is to try to simplify it. And so instead of trying to understand the population of black holes detected by LIGO and Virgo in the entire universe, maybe we should try to understand the population of black holes in our own Milky Way, which is also far from being well understood. So when we look at the population of known black holes, the vast majority of them come from LIGO and Virgo. So now we have hundreds of gravitational wave detections. most of them are by black holes. We also have masses for roughly 20 black holes in X-ray binary star systems. So these are close binary star systems containing a black hole and a companion star, which may be a neutron star or a giant, which is transferring matter onto the black hole. So we see X-rays that are formed during the accretion processes when the matter falls on the black hole. I think we have like 4 good examples of black holes in wide binary star systems in which there is no mass transfer rate and we observe no black holes. We think we observe no X-rays. So we say these are dormant black holes in that are not interacting. And we have only one example of an isolated black hole, which I'm going to talk about later. On the other hand, when you look at the predictions of the population synthesis models, for example, that particular model by OAUW, these models predict that roughly 90% of black holes should be isolated. About 7% of them should be in wide binary star systems, when no interactions occur. About 0.2% of all black holes should be in close binary star systems that are interacting with the companion. And about 0.2% of all of them should be in binary black hole systems that are going to merge within the Hubble time. So it's clear that what we are currently observing is just a tip of the iceberg of the black hole population in the Milky Way. And the goal of my projects that I'm running for the past few years is to try to understand that population, that huge population of black holes that should be out there in the Milky Way. Of course, this has been a topic of a lot of research, and people have been trying to push and find more and more black holes over the past few years, but very often these efforts are fruitless. So some of you may remember that paper from 2019 by the Chinese group, which claimed the discovery of a 68 solar mass black hole. And like within a week or two, this discovery turned out to be wrong because simply they calculated they had wrong measurements of radial velocity. So that discovery turned out to be wrong within weeks. In the next few years, there were more similar cases in which people claimed they had found a black hole in a binary star system. And within weeks, another paper came up and said, well, you're wrong. So this only shows you how difficult it is to find these objects. And I think now we have at least 3 good candidates for black holes in binary star systems, or at least 3 candidates that were not disproven by someone else. All of them were detected by the KAGRA satellite, and then confirmed spectroscopically. Anyway, these are black holes in wide binary star systems with very long orbital periods, longer than half a year, up to 12 years. And we will hear more about these discoveries, I hope, within a month or so. But clearly, there should be a large population of isolated black holes in the Milky Way, and it would be nice to try to find them. So this is why we have to develop some methods to try to find these objects in the Milky Way. I think one of the best methods is to try to use gravitational microlensing to find these objects. Because we are here in Warsaw, all of you probably know a lot of gravitational microlensing, but I see some students here, so just a quick reminder. Microlensing is an effect predicted by Einstein's theory of general relativity, which tells us that the light may be bent and deflected by gravity of massive objects. So suppose that we are observing a distant source of light It may be a star in the galactic center or a star in the Magellanic Clouds. And suppose that we have another object that is moving right between the source and the observer on Earth. The gravity of this lensing object is going to bend and deflect the light coming from the source. As a result, here on Earth, we are going to see a transient brightening of the source star. We call these brightenings gravitational microlensing events. What is important is that microlensing doesn't depend on the brightness of the lensing body. And so this method allows you to detect objects that are dark, that do not emit any light, objects such as neutron stars or black holes. On the other hand, duration of microlensing events depend on the mass of the lensing body. So generally, the higher the mass, the longer the events. So typical microlensing events by stars have timescales of a few weeks, roughly 20 to 30 days. Microlensing events by planets should have very short timescales, roughly about a day, maybe a few hours. And we expect that microlensing events by stellar mass black holes should have timescales of a few hundred days, 100 to 200 days and longer. This animation shows what happens during microlensing. So here we have the lens in the center, and the gray dot is the source that is passing relative to that is moving relative to the lens. We don't see the source. We see its two images that are shown here in blue. But usually these two images are so close to each other that we cannot really resolve them. So what we can do only is to measure the combined brightness of the two images, which changes with time, as shown here on this right-hand plot. And we can measure the combined brightness of the two images. These are microlensing events. These two images are called the minor and major image. One of them is located inside the Einstein ring. The other is located outside the Einstein ring, which has typical angular radius of roughly 1 milliarc second. So the images are also separated by roughly a milliarc second or so. They are so close to each other that we cannot resolve them with normal telescopes. But as I said, we can combine, we can measure the combined brightness. There are several experiments that are trying to search for microlensing events, and of course, one of them is OAUW, which stands from the Optical Gravitational Lensing Experiment. Of course, this is the project run at our observatory for more than 30 years as of now. So we are using our telescope to observe the densest regions of the sky, the galactic center, the entire Milky Way plane that is seen from our observatory. And we are also observing the small and the large Magellanic Clouds. These are two nearby galaxies. Over the past decades, we detected more than 24,000 microlensing events. Of course, you can say that some of them must have been caused by black holes, and that is true because we estimate that roughly 1% of all microlensing events should be caused by black holes. However, we have only one confirmed candidate, one confirmed black hole for microlensing. Why is that? The reason is that for microlensing events, it's very challenging to measure the mass of the lens precisely. This is because if you want to measure the mass, you have to measure these two quantities, Einstein radius, and the other quantity is the microlensing parallax. You can measure the microlensing parallax from the light curve. it can be observed as a modulation in the light curve caused by the orbital motion of the Earth around the Sun. So usually we can do that, and for at least for the long time scale microlensing events, we can measure the parallaxes precisely. But the problem are Einstein radius measurements, which are extremely difficult for if you are using only photometric data. And this is why we had only, actually, well, this is why we had only one black hole in among 24,000 microlensing events discovered by OAUW in the past decades. So fortunately for us, there are like new techniques that we can apply to measure Einstein radii for a large sample of microlensing events. And I'm going to spend like much of my talk discussing these new developments. One possibility is to use astrometric measurements, for example, with the Hubble Space Telescope or with the Gaia satellite. The other possibility is to try to resolve microlensing images using interferometry. And I'm going to talk about that too. So astrometry, of course, as I mentioned, during microlensing events, we observe the change in the brightness of the event, but we also can measure the change in the position of the source star in the sky. So as these two images are formed, the brightness is changing, and so their like mean position is also changing. So in principle, we can measure the mean position of the event on the sky and try to see this deflection of its position due to gravitational microlensing, so astrometric microlensing effects. These effects are tiny because the maximal astrometric deflection is roughly 1/3 of the Einstein radius, which is already on the order of milliards seconds. But fortunately for us, the largest deflection occurs well after the peak, so we can plan our observations well in advance. And also this astrometric deflection falls relatively slowly, like 1 over the length separation, which basically tells you that these effects can be detected for quite a long time after the event. And the first microlensing event for which these effects were robustly detected is OAUW 2011 batch 462. This was quite a long time scale event. You can see it's like the time scale was about 240 days. So one of the longest events during that year. And we observed this event using the Hubble Space Telescope for more than a decade. So we started observations back in 2011. The last data set is the last images are from 2022. And these lower images show the HST data, HST astrometry, so precise positions of the source star relative to background stars. These data were analyzed by two teams. One of them was led by Kailash Sahu from the Space Telescope Science Institute. And another team was led by Casey Lam, who was at the time at Berkeley. And as you can see by eye, these two measurements, these two groups, came up with different measurements. Specifically, Sahu found that the lensing body had a mass of roughly 7 solar masses, so a black hole. But Casey Lam found that the mass of the lens was somewhere between 1.6 and 4.4 solar masses. So maybe a black hole, maybe a neutron star, who really knows? So there was some serious problem, and we wanted to try to understand what was going on. This is why Andrzej Wdowski and Andy Gould started to look deeper into that event and try to understand why we had this discrepancy. What we found is that you can measure the direction of the relative length of source proper motion from the light curve of the event. So these are our OAUW data. And the direction of the length source proper motion measured from the OAUW data. You can repeat the exercise for the HSD data, for the circular reductions, and for the KC-LAM reductions. And immediately, this tells you which group was right and which group was wrong. So we found that circular reductions were correct. Using our improved autometry, we found the mass of the black hole about 8 solar masses. So this was the first black hole, the first isolated black hole discovered using microlensing. So why there was this problem? Why was this discrepancy? It turned out that our microlensing events, which is shown here in the center of these plots, had a very bright companion star that was really close, like closer than half of arcsecond. And the bright companion star biased astrometric measurements that led to wrong measurements by one of the groups. Of course, this was like one and only example in which you could use astrometric microlensing and Hubble Space Telescope observations to detect that events. But of course, Hubble Space Telescope observations are costly. You have to wait like 10 years for them to make the measurement, which makes things not very nice. But fortunately for us, we have Gaia, which is a space-based telescope that is measuring very precise positions of all stars, about a billion stars in the sky. Gaia is like observing all stars, so at moderate cadence, but this is fine. You can use the Gaia data to try to search for astrometric microlensing effects. But the problem is that because Gaia observations are at a really low cadence, we have to supplement them with high cadence autometric observations, for example, from OAUW. And our estimates that are that we should do that for at least 50 to 100 microlensing events. So we hope that once Gaia data become public, perhaps in 2026, we will be able to combine these two data sets, OAUW and Gaia, and so measure the masses for at least 3 black holes in the Milky Way. The other way of trying to measure the Einstein radius is to try to resolve the images of the microlensing source. And we can do that with interferometry. Quick recap, we have some students in the audience, so quick recap. We know that the light behaves like a wave. So if we have a coherent source of light, that light goes through slit, and that light goes through 2 slits, each of the slits will become a source of its own wave. These 2 waves are going to interfere with each other, and what we are going to see on the screen is the fringe pattern. So we can see some bright spots in which 2 waveforms are combining. And we can also see some spots on the screen in which the 2 wavefronts are canceling each other out. So we see this fringe pattern on the screen. This is another picture of that. So again, we have the source of light, 2 slits, and what we observe on the screen is the fringe pattern, the places of bright and faint spots. However, when we have like 2 sources of light, perhaps 2 images of the microlensing source star, then each of the sources will produce their own fringe pattern, which is going to combine. And what we are going to see is just more complicated fringes. Instead of thinking of slits and all that physics, we can use telescopes to observe the same object in the sky. And then we can combine the light from the two telescopes to obtain the same fringe pattern. From the mathematical point of view, it's a complex quantity that depends on our image, the shape of the image that we are going to observe, and the positions of the telescopes relative to the object we are looking at. But anyway, we know where our telescopes are, so we can easily calculate that. And we can start by studying the fringes, we can try to infer the shape of the image of our source star, of our microlensing events. In reality, it's better to have at least 3 telescopes instead of 2, because we have some random phases that can be introduced at each arm of the interferometer. So yeah, the visibilities that we are observing, the fringes that we are observing, depend on these intrinsic phases due to the shape of the source star, but also some random phases that are introduced by, for example, packets of warm air. And when we combine these 3 visibilities, we get the bispectrum, which has a phase known as the closure phase. So in practice, we have one particularly well-designed interferometer, Gravity. This is an instrument that combines the light from 4 8-point-meter very large telescopes. So we are like using these 4 giant telescopes as one telescope. We are observing the same target using all 4 telescopes. And because the separation between telescopes is like 200 meters, we can resolve objects that are really close to each other, like 2 up to 50 milliarc from each other, which is ideal for microlensing, because we expect that separations between the microlensed images should be roughly the same. But the problem with Gravity is that it can observe only really bright stars, like 9 up to 10 magnitudes. And this is because air atmosphere is not really stable. So we have some fluctuations in the atmosphere. We have vibrations of the telescope itself. That limits the exposure times, and it also limits the brightness of the objects that we can observe, up to 9 to 10 magnitudes. And actually, there aren't many events that are that bright. Here I have some examples that were really bright. One of the events reached like 11 magnitudes in V. The other was like 9 magnitude, reached the 9th magnitude. So these were like special cases, really bright events. And in these 2 cases, people actually were able to use gravity to resolve the microlensed images, to measure the Einstein radius, and so the mass of the lensing object. What I really want to point out is that these measurements are really precise. So you can measure the Einstein radius with precision from like 0.5% up to 1%. And the precision of the mass actually depends on the precision of the parallax, but still you can achieve like 2.5% precision in these measurements. So really high accuracy. But again, the problem was that we could use gravity for observing only really bright microlensing events, which are extremely rare. So this shows the number of microlensing events brighter than some threshold magnitude. So like typically every year we have maybe 2 or 3 microlensing events that are bright enough to be observable by gravity. But fortunately for us, there was like a new development at the ISO and an upgrade to gravity. Thanks to that upgrade, we can observe fainter microlensing events as long as we have like a bright star, like a reference star somewhere nearby. And because we are in the galactic center, in the galactic bush, there are like plenty of bright stars in the neighborhood. So thanks to that development, we can now potentially observe like 70% of all microlensing events that are out there. There are further upgrades. Actually, this year, as we speak now, ESO is upgrading the adaptive optics system at Gravity, and that again will allow us to observe fainter microlensing events. And so I suspect that within next years, we should be able to see, we should be able to observe like dozens of events every year. We started that project last year in 2023 together with Antoine Merant from ESO and Subodong from Peking University. We started using gravity and gravity-wide to try to observe as many microlensing events as possible. Last year, we observed several microlensing events. Here you can see our target list. This year, because of the upgrades, we didn't do much, unfortunately. But last year, we were lucky to, for the first time, use gravity-wide, this new mode, to resolve microlensed images for microlensing events over 2023 batch 61. Again, this is the light curve of the event. We observed it twice with gravity. One observation was before the peak, the other after. In two cases, like during the two epochs of observations, we were able to measure the closure phases. So each color corresponds to a different triangle of the telescopes. But during two epochs of observations, we are able to see the closure phases, we are able to see the fringes. So we could model these fringes to get the Einstein radius. So these are our results. We could like reconstruct the microlensing system. And again, in the center, we have the lens. The dashed circle is the Einstein radius. This gray path, this gray line is the path of the source related to the lens. It's curved because of the parallax. And there are like two reconstructed images per every epoch of observations. We are able to measure the Einstein radius, the mass of the lens and its distance. In this case, it's some boring main sequence star or a white dwarf. It's not a black hole, of course, but it shows us the capability of this new instrument, and it demonstrates that we will be able to use it in the future to make these measurements routine. And again, I want to point out that these are really precise measurements. So we measure the angular Einstein radius with precision of 0.7% and the mass with a precision of 2.5%, which we consider really like a good job. Yeah, and basically this summary, I already told that we will keep observing microlensing events with that instrument during the next years. We hope that in the next year, all upgrades will be finally finished and we will have the upgraded instrument with improved sensitivity. What is really nice is that with interferometry, we don't have to wait like 10 years, like in the case of the Hubble Space Telescope. We have observation within an hour or so. So we hope that in the next years, we will be able to resolve microlensing images for dozens of microlensing events. And we hope to increase the sample of isotoped black holes with these new observations. Okay, so we started this project a few years ago, and we hope to have the results in coming years. And I'm going to change topics a bit. But again, starting with gravitational waves and LIGO Virgo detections. Some scientists think that the black holes detected by LIGO and Virgo are really strange, and they cannot be really result of normal astrophysical evolution of massive stars. And so some people suggested that maybe these are primordial black holes, like created in the very early universe. And perhaps the black holes detected by LIGO and Virgo are dark matter. And as crazy as it may seem, some people take it seriously. So the first papers about that were published in 2016, right after the first gravitational wave detectors were gravitational wave events were announced. These papers have more than 1,000 citations as of now. So and if you look at the papers in the ADS with the primordial black hole phrase in the abstract, the number of papers is like growing exponentially. And actually now we have like one paper a day about the topic. So this only shows you that some people take it seriously, and so we should try to check if that's true. So unlike stellar origin black holes, which formed by evolution of massive stars, primordial black holes may have formed in the very early universe, even before first stars appeared, actually before atoms were created. So the universe had a form of a soup of elementary particles like quarks, gluons, leptons, and all such elementary particles. We think that this early universe was not ideally uniform. There were some small density perturbations, then some density fluctuations within it. We think that these density fluctuations grew as the universe grew, and they gave rise to the structures that we see now in the universe. So the first galaxies, galaxy clusters, and so on. But it is conceivable that such density perturbations may have had large enough amplitudes that they collapsed under their own gravity, and so created black holes. These black holes are called primordial black holes. As you saw, there are like thousands of papers about the topic, and probably every paper has their favorite formation mechanism. But one particularly like appealing idea is that these objects form during phase transitions in the universe, when we have some events in the plasma that change the equation of state, that change the speed of sound, and so on. So, for example, the coupling of W and Z bosons from this plasma may have gave rise to formation of objects, formation of black holes with masses of planets. This is this peak. Transitions of quarks into hadrons may have led to the formation of objects with masses roughly 1 to 30 solar masses. So perhaps LIGO Virgo mass black holes. And annihilation of positrons and electrons in the plasma may have gave rise to supermassive black holes with masses millions of times larger than that of the Sun. You probably know that the James Webb Space Telescope has recently measured masses of black holes in very early, very young galaxies. And these masses are suspiciously high. We don't know why. Perhaps they were seeded by primordial black holes, who knows? So we wanted to test these ideas. This is a really popular topic. We wanted to sit on that and see what we can get from OAUW observations. Of course, we know that observations by OAUW and other microlensing experiments basically ruled out compact objects as dark matter. These were the works by Łukasz and Patrick Nisserand, which basically showed that you cannot have compact objects in dark matter with masses from 10⁻⁷ up to roughly 10 solar masses. But LIGO and Virgo black holes had masses of 30 solar masses, 100 solar masses, that were much higher than the limits we got from microlensing at the time. And of course, why is that? Because when we have a massive black hole, it is going to produce very long timescale microlensing events. So for 100 solar mass black hole, we expect like events with timescales of 2 years. For 1,000 solar mass black hole, we expect timescales on the order of 6 years. For 10,000 solar mass black holes, it's like 20 years or so. So the problem was that these early experiments didn't have enough sensitivity to very massive black holes because they weren't long enough. They didn't observe long enough to be sensitive to those really long timescale microlensing events. But of course, we have OAUW has been observing the sky for decades, for more than 20 years. And actually, some of the stars in the Large Magellanic Cloud had, well, they had like 20 years of photometric data. So we wanted to use this data to try to search for those long timescale microlensing events to see if they are there in the sky. We had roughly 30 million stars in the central regions of the Large Magellanic Cloud. They were observed for 20 years. Another 30 million stars located in the outer regions of the LMC. They were observed for only 11 years. So in total, about 60 million stars, 60 million light years. Of course, there are much more stars, many more stars, because with ground-based observations, we cannot resolve close pairs of sources. So we estimate, by comparing our observations with high-resolution imaging from the Hubble Space Telescope, we estimate roughly, we had roughly 80 million sources in the LMC. In that data set, we detected only 13 microlensing events. You can see some example light curves on the left. All of these events have short timescales, shorter than 200 days. And if you think about it, you can explain all 13 microlensing events we detected by stars in the Milky Way and by stars in the Large Magellanic Cloud. These stars are lensing other stars in the Large Magellanic Cloud. So there's no need to invoke primordial black holes to explain our observations. We didn't see any long timescale events with timescales of years and that may have been caused by LIGO Virgo mass black holes. But we had really large sensitivity to such objects. So we ran really extensive simulations to make sure that we are able to find many of these long timescale events. These are the results of our simulations. A detection efficiency as a function of the event timescale. So as you can see, we could detect events with timescales as long as 8 to 10 years. So should there be any such long timescale, should there be any very massive black holes in the Milky Way, we should have detected at least some microlensing events by these objects. We had no detection, so we could convert it into upper limits on the frequency of such objects in the Milky Way. So on the x-axis, we have the mass of the compact object, and on the y-axis is the fraction of dark matter that may be made of such objects. Less than 1% of dark matter is made of 10 solar mass objects, less than 3% is made of 100 solar mass objects, and less than 11% is made of 1,000 solar mass objects. So clearly these limits are much stronger than what we had previously, and they also extend to much higher masses. And I don't have much time, short thing. So you probably know that in the last few years, we have been discovering really short timescale microlensing events in the galactic center. We think they are either free-floating planets or planets on wide orbits. It's not only OAUW. We have like 3 major microlensing experiments, and every experiment, each experiment, OAUW, KMKnet, and MOA, each of these experiments is finding short timescale, small Einstein radius microlensing events in the galactic center. We think that these free-floating planets or wide orbit planets are quite common. There are roughly a few such free-floating planets for every star in the Milky Way. But perhaps they are not planets. Perhaps they are planetary mass black holes. And again, this idea may seem crazy, but there was this Japanese paper that claimed that if our short timescale microlensing events are planetary mass black holes, then those black holes should comprise from 1% to 10% of the whole dark matter in the Milky Way. And again, as crazy as it may seem, this paper has 300 citations, which is like more than my original paper about OAUW discovery of short timescale events. So this shows you that some people take it seriously. We wanted to test idea. Maybe we wanted to find planetary mass black holes in the LMC. So we conducted a special survey of the large and the small Magellanic clouds. We observed the clouds at a very high cadence. So we observed the stars in the SMC and LMC with a cadence of 60 to 20 minutes. We observed roughly 35 million source stars and continued and carried out these observations for 2 observing seasons. So almost 2 years of data. We found some, well, when we look at the data, we found some interesting objects, but if you look more closely, none of them is a microlensing events. And we concluded that we have no short timescale microlensing events in our high cadence data. This again can be translated into limits on planetary mass black holes in the Milky Way dark matter halo. We rule out pretty large chunk of the parameter space. We were able to demonstrate that the short timescale events that we detected in the galactic center are not black holes. These are most likely planets. But with these new observations, we basically rule out all kinds of compact objects as dark matter at 1% level, all the way from asteroid mass up to about 10 solar masses. So this is like 11 orders of magnitude. And I think this will be like great legacy from OAUW. So to summarize, I hope to convince you, I hope I convinced you that we can use astrometric and interferometric observations of microlensing events to study the masses of isolated objects, including the masses of neutron stars and black holes. And we hope that within the next 3 years, we should be able to measure the mass function of black holes. We should have enough measurements to measure the mass function of black holes. Our observations also indicate that LIGO Virgo mass black holes make up less than 1 to 3% of the whole dark matter in the Milky Way. So it's very likely that LIGO and Virgo is detecting astrophysical black holes, not primordial black holes. And we also found that the short timescale microlensing events that we see in the galactic center are, again, unlikely to be black holes, and these are most likely planets either free-floating or wide orbit planets in the Milky Way. And that's my summary. Thank you.
Thank you, Przemek, for a very comprehensive talk. Do we have any questions? Marcin, please.
Comment that you fulfilled the original task of the problem.
Yes, well, we think that, well, it will be really difficult to improve on these limits because you cannot really improve on this high mass end because it would require another like 10 or 20 years of observations, and it's hard to get. And we can really also improve on this low mass end because we are like fundamentally limited by finite source effects. And at some point here at 10 minus 10 solar masses, we are limited by the fact that the size of the black hole is smaller than the size of the wavelength of the light we are looking at. So we cannot really like push to lower masses of microlensing. So I think we'll like have these results for years from now. It will be really hard to improve on this.
And to the HSC, what?
HSC is the Hyper Supreme Camera, which is on the Subaru telescope. It was a project led by a Japanese group, which observed Andromeda Galaxy for 2 nights, but at a really high cadence. They had one observation every 2 minutes. So they aimed to find a very short timescale microlensing events in Andromeda. They didn't find any. Well, they had one candidate, but it's not really convincing. So they put these upper limits on asteroid mass or dwarf planet mass black holes in dark matter. And again, they are limited by the wavelength. Yeah, well, asteroid mass black holes, which perhaps you can think of some theories that can produce such objects. Yeah.
Let's move to the other question.
I must make this comment. Yes, of course, microlensing can detect planetoid mass primordial black holes, but if such planetoid mass black holes exist, they will collide with neutron stars and convert them to black holes of masses of about 1.5 solar masses. And this, of course, microlensing that you could easily, as we have heard, detect in the coming years. So there is a way to close this window, even for this super tiny primordial.
Yes, you're right. That if asteroid mass black holes exist, they should, as I demonstrated, they necessarily collide with neutron stars and convert them into low mass black holes. And like this whole project is aimed at measuring the masses of isolated objects in the Milky Way, the masses of neutron stars and black holes. So we hope to find similar objects. I think one of the biggest difficulties would be to distinguish between like 1 solar mass black hole or 1.5 solar mass black hole and neutron star. It is like the main challenge for us.
When we come up for that for the LIGO in the future. The problem, of course, is that there are small masses, so we don't have very good sensitivity for high frequencies, but the measuring differences if you have in environments and objects, there are tidal forces which are existing for 2 neutron stars. When you get a neutron star with a black hole, you can see this tidal forces. But the problem is with the small masses that our frequency, is set above 1 kilohertz is still quite bad. If it would be better, I would say higher masses, better.
I would like to go back to the first part of the talk. So you were saying 9 times magnitude. That's so any upgrade from that, because I'm kind of stunned by that, because I mean, if this is the limit, that would it be better with the adaptive optics or something? Because you don't have adaptive optics here, right?
Well, we have adaptive optics systems on those telescopes. So the fundamental problem is that the atmosphere the Earth's atmosphere is not stable and it fluctuates at a very short time scale. And that breaks the coherence of wave fronts that are coming from the star. The other problem are the vibrations of the telescope itself. The telescope structure is vibrating at a very high frequency. And this is why the exposure times are like 1 millisecond or a few milliseconds. So what really limits us here are these vibrations of the telescope structure and the atmosphere. This is why, but this is why we have not with PLT. You would have to build new interferometer.
This is technical.
This is a technical issue. You cannot really improve on that. But we have this gravity-wide system, so we can observe fainter objects like 15, as long as there is like bright star nearby. And in the galactic center, there are a lot of bright stars because it's a really crowded environment.
So to follow on that, how costly are these interferometric observations? I understand the exposure time is very short, but altogether the one observation, one data point that you produce, how much time does it take for?
It's roughly 1 hour observing time.
So
of course, we have to combine many. Well, we have short exposure time, but we have to repeat it many times. So typical exposure takes anywhere from half an hour up to 1 hour.
So like the OB is around
about 1 hour.
Any more questions, Lukasz?
That's impressive work, well done. And I'd like to go back to a couple of questions. Let's go back to this idea of this asteroid primary black holes, and then they form this one solar mass black holes from neutron stars. So would these, you mentioned to you as well, would they reside primarily in the galactic disk other than the halo?
Yes,
yes,
we can detect them. Well, we can detect them if they hit the neutron star, and neutron stars are in the galactic plane. So
maybe in that sense, maybe some of the events we see, which you measure and last for around 1 solar month, these might be actually these black holes.
Yes, but as I said, it's really challenging to distinguish a black hole from a neutron star at 1 solar masses.
Well, we could kind of wait 10 years when they separate, and any event observing them, trying to distinguish it after a black hole.
I don't think it's worse.
I don't think so.
It's nearby.
Is it pulsar?
And so then, kind of a similar question. So you showed this plot for the ages, how we predict years, right? And so the main peak actually is at 1 solar.
Yep.
And it's like few orders of magnitude higher than anything else.
Yeah.
So
Yes.
this should be our first worry, right? And you completely ruled that out.
Yeah. And I was able to rule that
How
out.
done a lot, together your limits and this plot.
I don't have this thought in my presentation, but if you assume that the mass function of primordial black holes follows that function, and you assume then you get a limit of 1%. You can explain 1% of entire dark matter by primordial black holes of that mass function.
Okay. It's almost 5, so I think, well, let me check if there are anything on Zoom. I cannot see anything, so I guess there is nothing. Okay. Thank you, Przemek. Thanks a lot for a very comprehensive talk. Thank you for the discussion. Let me also say that Przemek is also leading several student projects. So if anyone is interested from the student side, I hope
Sure.
the time will talk to any of you interested. Another comment is that there is a black notebook. Master students and PhD students are asked to put their names there. And so let me invite you also for the next week's seminar that's going to be given by Knut Olsen from Neuer Lab about the internal kinematics of Magellanic clouds. So we'll see each other here Tuesday 4 p.m. Thank you very much.